All right. All right. So, hello, everyone. Anyway, before I begin, I just want to thank the guys from KIS for allowing us to present at this event today. I'm Brent Gorin, and I am Segment Development Manager with Eaton. All right. Today's presentation is on artificial intelligence, smart technologies, and the impact that those technologies actually have on power, space, and cooling. Right. So the first thing that I notice when I look at this slide is that red telephone on the upper right-hand corner. And the reason why it grabs my attention is because I grew up with that technology, right? Right, I'm sure you did as well.
Yeah,
right.
Actually, my first phone is Rotary.
Yeah, right. Me as well, right? Me as well, right? But the thing is for its time, that was the best technology we had in the day. Right. And the most reliable technology as well, right? I just have to memorize 7 digits. I can call my best friend, my family members, right? Anyone, as long as I knew what their phone number was, and it doesn't matter how far away they were.
Yeah.
Right. Now, granted, if they were in a different state or different country, it'd cost a lot of money, right? But it wasn't.
No, you don't remember anybody's phone number.
Well, that's exactly right. It's different, right? Right. And the technology was so prevalent; it was in every single home, right? Every single home, and they had multiple phones like that, right? That's how prevalent that technology was, right? But anytime we have upgrades in technology, things change, right? And of course, that kind of technology has now been obsolete, right? It's been replaced with something like this, okay? And there's a real reason why it's been replaced by this, because the functionality that we have with a device like this is far superior than anything that used to be able to do, right? With that one, you have the ability to make calls. Here you can make text messages, emails, phone calls, video conference calls, right? It also has applications that you can use for your everyday business and so forth. In fact, it actually travels with me everywhere I go. I'm sure everyone else in this room, this is what they use every single day. It goes with you everywhere, right? It's a part of your lifestyle, right? Anywhere you go, this goes with you. Hopefully not in the shower.
I even have 2.
But here's the thing. The transition between that and this didn't happen in a day. All right. It took actually generations for that to happen. Right. But the concepts, right, behind this kind of technology was around for 60 years. Anyway, did you ever watch Star Trek back in the day?
Mm-hmm.
Right.
Yeah.
So you remember Star Trek, right? So they used to have communicators, right? They used to have communicators back in those days, right? And as you know, if somebody actually called you on a communicator on Star Trek, right? It would show up on a video display, right? So it's not as if they didn't have video, the idea of video. And being a Star Trek fan, what was the power source for the Star Trek Enterprise? Dilithium crystals. They knew about lithium technology 60 years ago, right? They just didn't know how to harness it, right? And that's really the difference, is the ability to harness this technologies to make something like this, right? The fact that we actually have a mobile chipset, we have our 5G network cells, right? LCD displays, right? That lithium ion battery that we have inside this phone, right? I mean, that all took time for it to come out, right? And frankly, it's the same thing with AI. Okay. AI is nothing new, right? You probably know this, right? When I went to school 35 years ago in university, I took courses in AI, right? Even my engineering grad thesis was on AI models. It's not new, right? What's new is the technology behind it that's actually making it possible to do all these different things, right? That we could potentially do with technology today, right? And there's, technically speaking, there's one company who's really driving that, right? And we all know who they are, right? I mean, there's a reason why NVIDIA was like a $80 billion company 6 years ago. Now they're worth $3 trillion, right? They have a 70% market share in the business, right? And we're all playing catch up, right? And, you look at all the different things that are capable of, with this technology. I mean, when most people think of AI, they're usually thinking about queries and responses from ChatGPT, but it can do a heck of a lot more than just that, right? Anyone been to Phoenix lately? No? Autonomous vehicles are a reality in Phoenix, It's not something in the future. And, we were just talking about this in 2018. That's the first conversations we're having of autonomous vehicles, and it's now a reality that fast. That's how fast this stuff has taken over. Medical imaging analysis, another really good example. When a radiologist looks at an MRI or a CT scan, they'll probably look at 50 different images a day, but they're really looking at a single image and doing a diagnosis on that one image based on what they see on it. Well, what AI can do is that they can discover patterns for thousands of images, right? And based on that pattern recognition, they can actually diagnose something before the human eye can actually detect it. And from that standpoint, they can detect cancer way before any radiologist has the ability to actually sort of see any of those on the scan, right? And that's the power that we have with the guide, okay? But with that, comes a little bit of an issue as these technologies start to grow, right? The power consumption needed to drive some of these GPUs that NVIDIA is creating is enormous. In fact, if anything, it's about 10 times what we're typically looking at today, right? You go into a traditional data center, we're typically looking on average 5 kW to 10 kW per rack. NVIDIA is producing racks already. This is the next generation, 120 kW load for a single rack, right? And as a manufacturer for power equipment, knowing the fact that this is coming out quickly, we have to make some adjustments to be able to handle some of these things, right? Right. So it's not just about power, right? It's also the intricacies of how we sort of make it work as a part of the whole power distribution network, right? And understanding the difference between what a traditional server looks like and what a new AI server is looking like is very important. So let's talk about some of the differences, right? So if I look at this traditional HP ProLiant DL360, which you'll find in almost every enterprise data center, standard it comes with two 800-watt power supplies, right? You can upgrade them to 1600 watts, right? If you compare that to this NVIDIA DGX H200 server, it comes with 6 power supplies, and they're 3300 watt. We do the math on that. Add them all up, it's 20,000 watts in a 7U frame, right? It's a lot of power, but it's not just about the power. Those power supplies run at higher temperatures. So the connectors that are inside those power supplies also potentially need to be changed, right? Typically, when we look at a connector on the side of a power supply, it usually uses like a C14 or C20 connector. The higher temperature ratings, that's not going to work. They have to be adjusted to either C16s or C22s, right? And if you do that, then the power cores that go into them also have to be adjusted. You can't put in a C19 into a C22. It has to be a C21. So that's also something to know. The other thing we know is that in traditional data centers, we're usually powering these boxes with 208, 120 volt power distribution. We're not doing that for AI servers. We're coming with 415, 240, right? Just because of the higher capacities, we need the higher voltage as well. And the next generation, potentially we're looking at 480, 277 directly, right? We just have to wait for the power supplies to be ready, rated for 270 watts. And then the last part of the specifics is the power supplies are getting very, very close to the circuit limit that they actually reside on. And that's probably the most important piece about this. And I'll get into that in the next slide. So what you're looking at over here is on the top left-hand corner is a server that Microsoft was displaying at the Supercompute conference last year in November. All right. This isn't a box that's for sale. This is actually what runs their cloud business, right? That box, I'll just call it a box, has 6 power supplies in it. On the bottom right-hand corner is the power supply rating for each one of those 6 power supplies. I'm not too sure if you can read that. Let me just laser pointer that if that works. You see that? No, I guess not. Anyway, it's right over here. Do you guys see that? 240 volts. 5,200 watts for one power supply. Okay. Now, it's a titanium plus 80 titanium plus power supply means that it's, it has to be at least 94% efficient at full load. In this case, it's 95% efficient. Okay. So 5,200 watts is what it needs to drive to the equipment, but that's not the input source. Input source is going to be 5% higher than that, which comes out to about 5,470 watts, right? So let's see what kind of circuit breaker I need to be able to actually drive, right? So if I went to like a 20 amp circuit breaker over here, right? Maximum continuous load gets derated by 80% is 16 amps. 16 times 240 volts is 3,840 watts. That's not going to do it. I can't put that power supply in a 20 amp circuit. I need to go to a circuit that's slightly higher, right? So the next rated circuit breaker is a 30 amp circuit breaker, 24 amps continuous power, 5,760 watts. Remember I said 5,470. It's at the limit. That power supply is at the limit of the circuit that it resides in, right? So the point I'm trying to make with all this is that when we look at AI servers, we have to have a circuit breaker dedicated for every power supply. I'm going to repeat that. You need a circuit breaker dedicated on every PDU for every power supply, right? So let's have a quick look at what that looks like in a rack, right? So on the left side is a traditional server distribution. I mean, quite frankly, it's not necessarily realistic because you would have mixed loads, but for the purpose of this presentation, it's fine, right? So, but let's just assume we got 30 of these ProLiant DL360s, right? 800 watt power supplies each. And let's just say on average, the load is never exceeds 500 watts per. Okay, so that's 15,000 watts continuous, right? So how am I able to actually handle that? Well, if I have a 208 volt, 60 amp, three-phase PDU, that's rated at 17.3 kW. That can handle 15 kW of load, right? Fairly effectively, provided that I actually have my power distributed properly across all these receptacles, because I only have 6 circuit breakers on these PDUs, right? And each circuit breaker is only rated for 3,300 watts, right? So I have to make sure that because they're shared receptacles on a single circuit breaker, I have to make sure that it's load balanced properly. Okay, and then I can actually effectively do this. Okay, but let's compare that to AI, right? Let me just switch sides here for a second, right? So on an AI box, remember, I need to have one circuit breaker for every power supply. So if you look at this 2U PowerEdge XC9640 liquid cooled rack server, right? It's 2U high. It has 4 power supplies in them, each rated at 2,800 watts, right? You put 21 of them in a rack, that's 84 power supplies. If I got 84 power supplies, I need 84 circuit breakers. Now you can sort of see the difference in size between all these PDUs, because I need to be able to have all these different circuit breakers. You see there's 42 on this side, and there's 42 on that side. And that's the only way to manage with AI, right? But the simplicity is this. I never have to worry about that load balancing issue that I had on that other one, because that power supply will never exceed that circuit breaker. All right, well, what about dimensioning and weight, right? So we got width, we got height, we got depth, right? We don't have any issues on the width side because it's going into a standard EIA 310D cabinet that has a standard 19-inch rail. So that's going to be consistent across the board, right? What about for height, right? Well, rack heights are standard too. You got 1U, 2U, 4U, 7U, right? That can be adjusted fairly easily, you know. It doesn't really matter if it's a traditional AI server. Typically, the AI servers are going to be taller, but it's nothing that we can't handle already, right? The racks are built for that. But what about depth? Okay, the standard depth on a traditional server is usually about 30 inches. Okay, on an AI server, they're going beyond 40 inches. Well, most of the cabinets that are out there today are 42 and 48 inches deep. I can't fit an AI server in a traditional cabinet, right? Even if it's like 42 inches deep on the server and I got a 48-inch cabinet, there's no room for any infrastructure. I can't put the cabling, the PDUs, or in the case of an AI server, I need a liquid manifold in the back. So it's not going to work, right? So we've actually introduced a brand new cabinet, got released a couple of days ago, 54-inch cabinet, right, to be able to meet the needs of AI. Okay. The other thing is because of the weight load that we have, and I forgot to mention that on the other slide, right? With AI servers, with all the different componentries that are inside of it, the power supplies are much bigger, we're typically looking at a 50% increase in weight per U. Right? So to handle the weight load, we've increased the static weight load from 30 pounds to 5,000 pounds in this rack. So there's a lot of more options that we now have now that we've introduced a rack specifically built for AI. Okay. What about cooling, right? So Jensen Huang, everybody knows he's the CEO of NVIDIA, right? He recently came out, did a little video or presentation where he announced the next versions of their DGX line of servers will be liquid cooled. That's a pretty bold statement. What I mean by pretty bold statement is nobody wants to do liquid cooling. Nobody wants to do liquid cooling because if you look even at the if you look at the hyperscales, if you look at the colos, they have built massive amount of infrastructure already built in place for air-cooled systems. It's going to cost them an enormous amount of money to switch to liquid cooled, right? So they don't want to transition to liquid cooled. But that bold statement was there for a reason, because he's preparing the industry to basically let them know that our next version of GPUs, they're not going to be air-cooled anymore, right? And I'll go into some of the reasoning why that is, right? There are both theoretical and practical reasons why we need to switch to liquid cooling, right? So that diagram that I had, and let me move to this side of here. This diagram over here is essentially a performance curve for a heatsink, an airflow heatsink, okay? And what you're looking at here is the thermal resistance of the function of airflow as air actually passes through the heatsink, okay? And that thermal resistance will drop until it gets to a point where it kind of flatlines. So you can sort of see that portion down there, right? When it flatlines, it basically means that regardless of how much airflow I actually push through that heatsink, I am actually no longer effectively taking out any more heat from that heatsink, okay? Now, I've talked to a lot of thermal engineers, and of course, right now, the best heatsinks that we make now have basically a thermal resistance that flatlines at about 0.1 Celsius per watt, somewhere around that range, okay? This one's actually quite a bit higher, right, 0.17, right? But at 0.1 Celsius per watt, what they've been telling me is that once the TDP, which essentially means thermal design power for the chip, goes beyond 350 watts, right, you need to use liquid cooling, right? Now I can tell you that the current Hopper chips that NVIDIA makes have a TDP rated up to 700 watts, and that Grace Blackwell's that'll be introduced later on in the year, 1200 watts. So it's not even in the range of what we're looking at for air cooling, and that's why they're making that announcement early. Okay, so when all this stuff gets released, everyone knows that this thing's got to be liquid cooled. So effectively, two different types of liquid cooling solutions out there. And I just say that generally speaking, because in reality, there's much more than this. But these are, if I were to generalize, we're basically looking at direct-to-chip liquid cooling or immersion cooling. So the difference between direct-to-chip is essentially we have some device known as a CDU or coolant distribution unit that basically pumps liquid, typically water, okay, because water is probably the most efficient liquid we have, okay, for cooling. And it pumps that liquid directly into the server through tubing, okay? Now on top of that chipset, we would have what's called a cold plate. So the tubing penetrates right through the cold plate, okay? And as it moves through that cold plate, it actually extracts the heat directly from the chip, right? And then, of course, that loop goes back to a heat exchanger, takes it out of the system, and then it returns back and it repeats the cycle. Okay? With immersion cooling, essentially, we're just basically putting the servers in a bathtub, right? Right? But that bathtub is filled with, a liquid that is non-corrosive, right? Non-conductive, right? Non-combustible, well, non-flammable. It is combustible, non-flammable, right? But that's typically how part of the advantage that you have with liquid immersion over DTC is the fact that you're actually cooling the entire unit, right? With DTC, you're actually just cooling chipsets. And with DTC, you still need to have fans inside the unit for basically to take the heat away from some of the other devices that are physically in there. So you're only capturing between 80 and 90% with DTC. With immersion, you're capturing the full cooling, right? And of course, the other advantage is you don't need any fans because it's all right. So moving on to smart technologies. How much time do I got left here? So sure. All right. Oh, we didn't time it.
It is.
We didn't start the timer. That's right. Oh, I got 40 minutes. Wow, this is great. All right.
I should do one.
All right. So smart technologies. All right. We're seeing some significant advances in smart technologies with regards to building automation. Okay. Both from a standpoint, I won't say both, but many standpoints, including energy efficiency, security, as well as user experience. All right. And this goes across multiple different verticals like hotels, college campuses, retail outlets, and so forth. Right. When I go into hotels, and I go into a lot of hotels, right? When I walk into my Hilton hotels that I go into now, not to just give any name brands, but I can walk in with this phone, right? Let me just put this down for a second. I can walk in with this phone, right? I don't actually have to go to the front desk, right? I do check in on an app on my phone, right? I get access to, not only do I get check-in, but I can get full access card lock on my phone as I actually go to it. When I walk into the room, my name is printed on the TV set. I have full control of the TV with all the channels. And in many of the rooms, I also have controls to the temperature set through the HVAC system and sometimes even the lighting in the room, right? So from a user experience, right, I can go in there, I have so much control right at I don't have to look for a remote control to get access to my TV, right? I don't have to phone downstairs if there's a problem with the HVAC system. I got the controls right over here, right? Everything's all lined up. But even with that, right, and you see the power on the user experience piece, but think about the energy efficiency standpoint. As soon as I leave that hotel room, right, the administrator has the same access that I do, right? So as soon as I check out, right, they can turn off the lighting, they can turn off the HVAC system, they can turn off the TV, right? And that saves them a lot of money from an annual basis from an efficiency standpoint. So we're seeing a lot of huge changes. I spend a lot of time at ASU. It's one of my accounts that I work on. They pride themselves in being leaders in innovation, right? And they're doing a lot of work, to basically do a lot of these things with smart technologies and doing building automation and so forth. They're helping them a lot with regards to some of the challenges that are faced of converting older buildings, to some of the smart technology, right? Retail outlets. I mean, you've all gone and seen some of these new scanners that they have, right? Point of sale type scanners, right? When they first came out, everyone's really angry. It's like, where did my cashier go? Why do I have to do my own groceries, right? Right? But, here's the thing. So now that we've seen that the stores are filled with these scanners, right? I don't have to go into lines anymore, right? As long as I have a small amount of stuff, right? Right? If I only have like less than a dozen items, I have to wait for an express line that's filled with like 50 people that I have to wait for, right? So I see the value of it. But I did try to see how smart these things actually really are, right? So I did a little test fairly recently where I went in front of a scanner and I scanned some bananas, and then I slipped the grapes on the scale just to sort of see what happened. You'd be surprised, right? Right? It stopped the transaction immediately. The AI detected what I tried to do, showed me a video of me trying to basically cheat the system, and then send a call out to the manager to come and look to see what I tried to do, right? So these things are getting really, really smart, right? All right, demo time. All right, so when we talk about smart technologies, typically the most common ones that I see are devices like these two guys, okay? Not to say that this is a PoE enabled one because I just took this one from home, but this is a PoE device, okay? Do you guys know what these are? Yeah, security camera, Wi-Fi access point. I picked this up on eBay for $10. Okay, now why was I able to get this for $10? This thing originally sold for $500. Because it's obsolete. All right, like all technology, they get replaced over time, right? And certainly for this kind of technology, they get replaced really quick. Okay, because of functionality and security upgrades and so forth, right? The other thing to note about this thing is that when this came out, or I shouldn't say when it came out, it still is. It's rated at a maximum of 18 watts. Okay. The new replacements are anywhere from 30 to 50 watts. Okay. Now you might not seem to think that that's a lot. 18 watts, 50 watts, who cares, right? If you're in a building, they got hundreds of these. If you're in a university campus, they got thousands of these. Now compare the difference. That's 18,000 watts versus 50,000 watts. That's a huge difference, right? Now, the other thing to keep in mind is how do these things get powered, right? It's all about this 802.3BT standard, right? Right? They're not getting powered from a wall like this. It's a single Ethernet cable that's providing both the network connection and the power to this thing. It's the switch that actually needs the power, right? So when we're actually designing, for our network closets, our IDF and MDF closets, okay, we need to take into account the fact that they're varying loads because these things are going to change over time, and they're going to hit that switch with increased power requirements, right? So when we go into an IDF and MDF closet, they typically have 1U, maybe 2U switches, and maybe stacks of them, right? But here's the thing, right? Those 1U switches typically have like a 750 watt power supply, maybe 1100 watts power supply. If I have a 48 port switch, 50 watts per port, that's 2400 watts. How am I going to be able to accomplish that with a device that actually only has two 1100 watt power supplies? It's impossible. Okay, right? You can't do it. So you have to upgrade to something that actually has the power capacity to be able to handle all that load. Okay, right? And that's where these modular access type switches come out, right? Because the power supplies in these things are rated for 3200 watts each, and there's 8 of them in that unit, right? And this manufacturer isn't the only one that makes them. There's multiple manufacturers that make these box, but that's why they're making these modular access switches, right? It's basically to handle some of those loads that you can't get from the 1U switches. Now, Cisco does make a switch that is stackable, right? That you can actually share those power supplies together, right? So it is possible if you do it with stack power, as an example, right? Or, if you buy multiple switches and you divide some of the shared load across them, I mean, there is ways around it. But eventually, as these things starts to grow, you're limited to what the power supply is in that unit. There's only so much power that you're going to be able to get out on a 1U switch, right? Unless, of course, they start making bigger power supplies for those 1U switches. Right? So here's the thing about modular access campus switches, right? It's a challenge to power, just like AI. 3,300 watts, or in this case, it's 3,200 watts, right? Again, that's the limit of the circuit that it's on, right? A 208 volt, 20 amp, which is what that is, all right? That's a circuit that maxes out at 3,328 watts. And those power supplies are rated for 3,200 watts each. So I need to have a PD. If I'm going to put PDUs on here, I need to have a dedicated circuit breaker for every single one of those, right? And the issue, the other thing is with regards to UPSs, right? How am I going to fit a UPS to handle 25,000 watts in an IDF or MDF closet? These are not data center switches. These are edge switches. These go with IDF and MDF closets, right? And there's no room for them. So that is, another challenge that we have, right? You go inside an IDF and MDF closet, there's no space for these things. You might have the space for the switch, but what am I going to do with power? They weren't designed to handle that much power inside a traditional IDF and MDF closet, right? You go back into the history of when these things were originally built, right? They were never designed to support stuff like this, right? They weren't designed to handle mission critical type applications. When we first started doing VoIP, it was like, phones. I mean, they weren't big conference phones like that one, right? But they were, feeders to a VoIP phone at somebody's desk that was maybe 5 watts each, right? But that wasn't necessarily considered mission critical. But if you're using built for building automation, for Wi-Fi access and security cameras, now it becomes mission critical. So I actually have to have these things protected by UPS. So the point I'm trying to make with all of this is, as you go through the changes of looking at these types of solutions, it's best to talk to people who know a little bit about power when you're trying to put these solutions together. I'm gonna end it here because I imagine I am pretty close to my end of time. Am I not right? Yeah, we're at 10 o'clock even. All right, so anyway, it's great to have this discussion with everyone. Glad to have time to talk to you. And
Thank you.
any questions? I still have 5 minutes for questions. Any questions?
Just make one comment that I think they're all really good concerns you listed, but the theoretical maxes like that you described is not how, especially in the switches, nobody lays them out. Nobody's gonna pack all PoE devices
all the
on there.
devices.
And power, they're not gonna power both rails of the power supply. They're gonna split one onto house power and one that can support it, right? And they're gonna.
But even if you did that, let's say you do that, what happens if you lose house power?
It's that.
Everything goes to UPS.
Right.
The entire load.
Right, but you don't design and put all of PoE devices onto that. You put it into a place that can be powered by half the amount of rail, right?
Mhm.
So I just like it's a very big concern, and
Yeah.
the sizing, especially with PoE like
Yeah.
I don't know what they were thinking, but
Well, you know that it's actually going to increase.
Power
Like
fridge.
802
I don't know why.
802.3 BT is just a start.
yeah, I know. It's
Next generation, we're going to be looking at higher than 100 watts. And when you get there, how are you able to like the types of things we're looking at AI? Like I'm looking at it from a user standpoint, right? The functionality that we have in here requires a certain amount of energy. And as soon as we start adding, newer feature sets, it's going to require more power. And that was the whole point, right? I mean,
yeah.
this replacement, this was 18 watts. The new ones are like the next generation, it's going to be even higher than that.
Yeah, and I saw a security mag lock that's PoE,
Yeah.
and that's 0.80, like to be able to do a mag connect. And
Yeah. And they're hitting the limits, right? And once they hit the limits, it's just like that NVIDIA thing what Jensen was talking about. Is like, you got to go to liquid cooling. And now everybody like us, we need to make adjustments. The problem is that our infrastructures are built to handle those kinds of things, right? All right. Any other questions? Yeah, go ahead.
Yeah, I have a question. So let's say it's a company that is kind of limited by budget. They're trying to upgrade their technology to the newer technology that's coming out because of security, ease of use, all that kind of stuff, right? So if they're upgrading this kind of technology over a period of time, how would they be able to, I guess, space out what kind of upgrades are prioritized first due to their budget limitations?
So the way I would look at it, like I do all infrastructure projects, is I basically say, where do you think your maximum load is going to be in a certain period of time before you think you have to change? Because typically they have budgets that they sort of assign before they, I have, I'm going to make an infrastructure change and I expect this thing to last for 5 years. So if it's going to last for 5 years and that's your plan before you have to make your new budget, right? Then you have to plan for that 5 year. And then that's where you max. And you basically make an assessment, okay, my average port density is going to be 30 watts per port on average in year 5. And then I build to that. Because if you don't, the risk is that you get to your 2 year point, right? And if you didn't hit that infrastructure, it's like, oh my goodness, now I'm going to hit with like these massive construction costs to redo everything that I didn't budget for. Hopefully that answers your question.
Yeah.
All right, good. Let's, I guess we can end it.